guys, Spider-Derivative Man here, talking to you about finding derivatives using limits. Now here's a question. Why didn't Superman like going out after dinner? Because he was afraid of kryptonite.
First vocabulary term is a tangent line. That's a line that touches a curve at one point without crossing through it. So here you can see we have a black function, and then this red line right here is a tangent line because it touches the black function at one point, point P, the point of tangency, and then continues on. It doesn't go through the black function. It doesn't cross through it at 2 points. It just touches it at one point and then continues on. Over here we have our red function, and the blue line is tangent to the curve at this point, the point of tangency, but it also crosses through at another point. So technically this line we cannot consider a tangent line. We're going to call it something else. But we can say that this blue line is tangent to the curve at this one point because it goes up, touches the red curve at one point, and then continues on. Now, because it touches the curve at 2 points, you can call it a secant line. A secant line is a line that intersects a curve at 2 points. So here we have our blue function, and this purple line is our tangent line because it goes up, it touches the blue function at 1 point, and then continues on. Remember, this is the point of tangency. The red line, you can see, intersects the blue function at 2 points. Because of that, we call that a secant line. Same thing over here. We said this blue line is tangent to the curve at this point, the point of tangency, but because it intersects the curve at 1, 2 points, we technically call this blue line a secant line instead of a tangent line. Now, the derivative of a function at x is the instantaneous rate of change, or amount by which a function changes at a given x value. The derivative of a function is equal to the slope of the tangent line at a given x value. Now, the first thing I want you to do is note that there's 3 things here that mean the exact same thing. The derivative of a function at x is the same thing as the instantaneous rate of change at a particular x value, which is the same thing as the slope of the tangent line. So all 3 of these things mean the exact same thing. So now let's look at our 2 examples down here. In this first example, we have a blue curve. This is our function. And let's say I want to find the instantaneous rate of change, the derivative of the function at x equal to 1. So I want to find the slope of my function at one particular x value, x is equal to 1. All I have to do is draw my tangent line to the curve at that particular point. So here we have this red tangent line that goes up, it touches the curve at one particular point, and then continues on. This tangent line, if I were to find the slope of it, it will give me the derivative of my blue function at x equal to 1. It will give me my instantaneous rate of change at one particular x value, x is equal to 1. It'll give me the slope of my function at one particular x value, x is equal to 1. That is what this is talking about. So anytime you hear derivative of a function at a particular x value, it's talking about the slope of the function at that particular x value. It's talking about the instantaneous rate of change at a particular x value. It's talking about the slope of the tangent line. All of those things mean the same thing. Now let's look at this example over here. Here we have our function in red, and our tangent line is this blue line. And it's showing you the tangent line to the curve at different x values. So as we increase in x values, you see how the tangent line to the graph changes as our x values increase here. Now let's talk about the definition of the tangent line with slope m. So all this is saying is that if you were to evaluate this limit, the alternative form of the derivative, the limit as x approaches c of f of x minus f of c all over x minus c, it will give you the slope of the tangent line to the graph at point c comma f of c. We also want to note again that the slope of the tangent line to the graph of f at point c comma f of c is the slope of the function at x is equal to c. It's the derivative of the function at x is equal to c. It's the instantaneous rate of change of the function at x is equal to c. Remember that. So the way we're going to visualize this is with a graph. So we have our function in blue here, and our goal is to find the slope of our blue function at a particular x value, x is equal to c. So that's what we're trying to find. Now remember, the slope of our blue function at the given x value, x is equal to c, is the same thing as the derivative of our blue function at x is equal to c, which is the same thing as the instantaneous rate of change of our blue function at x is equal to c, which is the same thing as the slope of the tangent line to the graph at x is equal to c. So that last one is what we're going to use to help us here. So here's how we're going to do this. First, look at this right here. This expression, you should be able to see, is kind of like the slope formula, right? We have a y value minus a y value over the change in the x values. That's delta x. That's the change in x. So we have a slope formula that we're taking the limit of. Now, how does this work? Well, my goal here is to eventually get the slope of the line tangent to the curve, our blue curve, at this particular point, c comma f of c. Now, to do this, I'm going to first draw a secant line. And that secant line is going to go through my point, c comma f of c, and it's also going to go through another point. And this point has an x value that's a certain distance away from our initial x is equal to c value, right? It's delta x away. So we say that this x value is c plus delta x. So this point is going to be at c plus delta x, comma, and then the y value is just going to be whatever you get when you plug in c plus delta x for your function, so f of c plus delta x. So I have 2 points now. One point is at c comma f of c, and the other point is at c plus delta x, comma, f of c plus delta x. Now, how do I get the slope of this secant line? Well, I use the slope formula, which is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So f of c plus delta x minus f of c, oh, that's what's up here, over c plus delta x minus c. Well, the c's are just going to cancel out. Oh, okay. So I am creating the slope of this secant line. But let's say I want to keep moving this secant line so that this point is closer and closer and closer to my point of tangency that I want, c comma f of c. Well, if I make delta x shrink, if I make it smaller, then these points are going to keep getting closer and closer and closer together. And if they get so close to each other that delta x is basically shrinking to 0, then what I'm getting is the slope of the tangent line. So that's exactly what this is saying. It's saying that if you create that slope of the secant line and shrink your delta x so that it's basically 0, then you end up getting the slope of the tangent line. So that's how this works. That's how the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x gives you the slope of your function at a particular x value, the derivative of your function at a particular x value, the instantaneous rate of change of your function at a particular x value, the slope of the tangent line at a particular x value. So now let's talk about the definition of the derivative of a function. So that's basically what we were just talking about. Remember, the slope of your tangent line, the slope of your function, the derivative of your function, the instantaneous rate of change of your function are all one and the same. Here we have the derivative of f at x, f prime of x, is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Now, some people write this where instead of writing delta x, they write an h, and it means the exact same thing. The limit as h approaches 0 of f of x plus h minus f of x all over h, it's the exact same thing. I just use delta x because it helps you visualize what we were talking about earlier. Now, this right here, if you were to take the limit as delta x approaches 0 of this, you would end up getting a function. Let's say if you had a function, x squared, and you did this process, the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x, you would end up getting f prime of x is equal to 2x. So that's a function. You get a function out of this. This one right here, same thing, except we don't really use this that often. What does use this is a calculator. So your graphing calculators actually use this in order to calculate the derivative of a function. We're not going to use this that often. We just need you to recognize that this also gives you the derivative of a function. Now this last one is f prime of c is equal to the limit as x approaches c of f of x minus f of c all over x minus c. It's also called the alternative form of the derivative, and we'll talk about this more in a second. But what I want you to get from this is that this up here, if I were to find the derivative using this method, it would give me a function. Again, if my function started as f of x is equal to x squared, after doing this process, I would end up getting f prime of x is equal to 2x. But here, let's say I have f prime of c. C is a particular x value that I'm going to plug in. So if I do this, it's going to give me the slope of the function at a particular x value. It's going to give me a number. So if I use this, the alternative form of the derivative, it will give me a number. It will give me the slope of the tangent line to the graph at that particular x value, c. It will give me the instantaneous rate of change of the function at x is equal to c. It will give me the derivative of the function at x is equal to c. Whereas up here, you get a function out. And you could use that function to find the slope at any given x value, the derivative at any given x value. Whereas here, it's just giving you one number, and that number is the slope of your graph at that x value. So now let's talk about the alternative form of the derivative a little more. The derivative of f at c is f prime of c is equal to the limit as x approaches c of f of x minus f of c all over x minus c, provided this limit exists. Also note that the existence of the limit in this alternative form requires that the one-sided limits, the limit as x approaches c from the left of f of x minus f of c all over x minus c, and the limit as x approaches c from the right of f of x minus f of c all over x minus c, exist and are equal. So this works similarly to the delta x one that we were talking about earlier. The only difference is this time it gives you a number. It gives you the exact slope of your function at that particular point. It gives you the exact slope of the tangent line to the function at that particular point. It gives you the instantaneous rate of change at that particular point. It gives you the derivative of the function at that particular point. So again, the way this works is you have a point, c comma f of c, and that's where we want to find the slope. So what we do to find the slope of the function at this point is we choose another point on the function. We'll call it x comma f of x. We then draw a secant line going through those 2 points. I can then find the slope of the secant line by doing f of x minus f of c over x minus c. And that's what I have over here. Now, the way we get the slope of the function at this particular point, the slope of the tangent line, is we move x so that it's closer and closer and closer to c. We have x approach c. And that's what this is, the limit as x approaches c. So as x gets closer and closer and closer to c, our secant line slowly becomes our tangent line, to where as x approaches c, we eventually have the slope of the tangent line instead of the secant line. So that's what this gives you. Now let's talk about some derivative notation. So the derivative of f as a function of x looks like this. So we have the limit as delta x approaches 0 of delta y over delta x, the change in y over the change in x, which is exactly what this says over here too. The limit as delta x approaches 0 of f of x plus delta x minus f of x, the change in y values, over the change in x, delta x. That's the same as f prime of x. That's the same as y prime. That's the same as dy dx or d dx of f of x. All of these refer to the derivative of a function as a function of x, and that derivative will give you a function. So let's say you start with a function x squared, and you want the derivative of that. If you were to use any one of these, you will get a function 2x as your derivative of x squared. Whereas in this case, any of these will give you a number. It will give you the exact slope at a particular x value, c. So here we have the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. Notice the difference here. Instead of x, we're plugging in a number, c, for our x's. That's why it gives you a particular number, a slope of your function, a slope of your tangent line at that particular c value. Same thing here. We just talked about the alternative form of the derivative, the limit as x approaches c of f of x minus f of c all over x minus c. That will give you an exact number, the slope of your tangent line, the slope of your function at x is equal to c. Here we have f prime of c. Again, instead of being x, it's c. So it's taking the derivative and then plugging in a particular x value, c. That's why you get a number out. Same thing here.
With great power comes great example time.
Now example 1 says find the slope of the tangent line and an equation of the tangent line to the graph of the function at the given point. So let's first find the slope of the tangent line to this function at this given point. Now remember, to find the slope of the tangent line at a given x value, it's the same as finding the derivative of the function at a given x value. It's the same as finding the instantaneous rate of change of the function at a given x value. It's the same as finding the slope of this function at this given x value. So we want to find a particular slope, a slope at a specific x value. X is equal to -1. To do that, we're not going to use the first definition of the derivative. We're going to use the alternative form of the derivative, the limit as x approaches c of f of x minus f of c all over x minus c. This will give us a specific number, and that number is the slope of this function at this given point. So what c value do we want to plug in? Well, the c value that we want is just going to be the x value of the point of tangency. So our x value of our point of tangency is -1. So we're going to do the limit as x approaches -1 of f of x minus f of -1 all over x minus -1. Now, how does this work? What do I plug in? Well, f of x is just x squared plus 1. F of -1 is just x squared plus 1, but we're plugging in -1 for x. And then down here, x minus -1, we simplify to x plus 1. Perfect. Now let's simplify this. So -1 squared is going to be 1 plus 1 is going to give you 2. Now, we can just drop the brackets. X squared plus 1 minus 2 is going to give you x squared minus 1. Now, I can't plug -1 in yet. I still get 0 over 0. So can I simplify this any further? Yeah, x squared minus 1 is a difference of squares, and it factors into x minus 1 times x plus 1. Now the x plus 1s in the numerator and denominator cancel each other out, and I'm just left with the limit as x approaches -1 of x minus 1. Now I can substitute in -1 for x and evaluate this limit. So if I plug in -1 for x, I get -1 minus 1, which gives you -2. So I have just found the slope of the tangent line to this function at this given point. I found the instantaneous rate of change of this function at this given point. I found the slope of this function at this given point. I found the derivative of this function at this given point. It's -2. Now, if I want to find the equation of the tangent line to this function at this given point, I already know the slope and I already know the point of tangency. And all you need to create an equation of a line is just a point and a slope. So I know my slope, I know the point of tangency, I plug them into point slope form, y minus y sub 1 is equal to m parentheses x minus x sub 1, and I simplify. So let's plug this in. -2 is going to go in for my m, my slope, -1 goes in for my x sub 1, 2 goes in for my y sub 1. I then simplify. X minus -1 is the same thing as x plus 1, and you could just write x plus 1 in here and be done, because you can leave your answer in point slope form. Or you can put it into slope intercept form, y equals mx plus b, by making this x plus 1, then distributing that -2, then adding 2 to both sides, you get y is equal to -2x. This is the equation of the tangent line to the graph of this function at this given point. You can confirm that with your graphing calculator, and you see that if you graph y is equal to x squared plus 1 and our equation of our tangent line that we just found, y is equal to -2x, you see that this line, y is equal to -2x, is tangent to our function f of x at -1, 2. So we did it right. Perfect.
You try.
Okay, doing the same thing here. So first, we want to find the slope of the tangent line to this function at this given point. Because we want the slope at a particular x value, x is equal to 2, we are going to use the alternative form of the derivative, the limit as x approaches c of f of x minus f of c all over x minus c. For c, we're going to plug in the x value that we want the slope at, which is 2. That's the x value of our point of tangency. So we plug in 2 here, here, and here. Now, in for f of x, I'm going to plug in 2x minus 3 because that equals f of x. F of 2 just means we're going to evaluate this function at x is equal to 2, and then x minus 2, that just stays the same. Now we simplify. 2 times 2 gives you 4. Minus 3 gives you 1. Now, if we were to simplify this up here, 2x minus 3 minus 1 becomes 2x minus 4. We then try to plug in 2, we still get 0 over 0. So we need to simplify this a little bit further. So I can actually factor out a 2 from the numerator, and then the x minus 2's in the numerator and denominator cancel each other out, just leaving us with 2. So when you take the limit as x approaches 2 of a number, when you take the limit as x approaches anything of a number, it's just going to be equal to that number. So it's going to be equal to 2. So what have we just found? We just found the slope of the tangent line to this function at this given point. We found the derivative of this function at this given point. We found the instantaneous rate of change of this function at this given point. So next, we need to find the equation of the tangent line to the graph of this function at this point. Well, in order to find the equation of a line, you need a slope and you need a point. And we now have both of those things. Our slope is 2, our point is 2, 1. So we plug those into point slope form. Y minus y sub 1 is equal to m times x minus x sub 1. And I would be okay if you left your answer like this. This is technically the equation of the tangent line. It's just in point slope form. But if you wanted to put it in slope-intercept form, we just distribute the 2 to the x and the negative 2, add 1 to both sides, and we get y is equal to 2x minus 3. That is the equation of the line tangent to this curve at this given point. Wait, hold on. This isn't a curve, this is a straight line. And because it's a straight line, we end up getting that the tangent line to a line is just the exact same line. Oh, that's interesting. And it makes sense, right? If I were to graph a line and draw a line that's tangent to that line, you just end up getting the exact same line. Therefore, the equation of our function is the exact same equation as our tangent line here. For part B, we're doing the same thing. We want to find the slope of the tangent line first. So with the slope of the tangent line to this function at this given point. Again, because we want the slope of the tangent line at a given x value, c, or in this case 1, we're going to use the alternative form of the derivative. Now again, our c value is going to be the x coordinate of our point of tangency. So in this case, that would be 1. So we're going to plug in 1 here, here, and here for our c values. Now, what we're going to do is we are going to plug in f of x, which we know is x squared plus 4x. That's going to go in here. F of 1 is just this function when we plug in 1 for x here and here, and then x minus 1 stays like that. Now we simplify. 1 squared is 1. 4 times 1 is 4. 1 plus 4 gives you 5. We then, in the numerator, can drop our brackets, and now we have this. So we can plug in 1. 1 squared plus 4 times 1, that's going to be 5. Minus 5 is 0. Over 1 times 1, that's 0. So 0 over 0, no, that's an indeterminate form. So we got to try to simplify this somehow. Well, we actually know that this up here, x squared plus 4x minus 5, we can factor into x minus 1 times x plus 5. The x minus 1s then cancel each other out, and we're just left with the limit as x approaches 1 of x plus 5. Now we can evaluate our limit by taking the 1, plugging it in for x, and then simplifying. 1 plus 5 gives you 6. Now, what did I just find? I found the slope of this function at this given point. I found the slope of the tangent line to this function at this given point. I found the instantaneous rate of change of this function at this given point. I found the derivative of this function at this given point. I can then use this to write the equation of the tangent line to the graph at this point. To write the equation of a tangent line, I need a slope, which I have, and a point, which I also have. So then I take those and plug them into point slope form, and it looks something like this. Y minus 5 is equal to 6 times the quantity x minus 1. Now I can distribute the 6 to the x and to the negative 1. I can add 5 to both sides, and I get y is equal to 6x minus 1. This is the equation of our line that is tangent to this curve at this given point. If you want to verify that with a graph, you just graph your quadratic function x squared plus 4x. You see that parabola here, and then the line y is equal to 6x minus 1, we graph that, and you can see that over here is tangent to the curve right at 1, 5. Perfect, we did it right. Example 2 says find the derivative of the function by the limit process. So here we just have a function, f of x is equal to x squared minus 3x. And it says find the derivative. It doesn't give you a point of tangency. It doesn't say find the slope of the tangent line at a given point. So because we're not trying to find the slope of the function at a specific x value, or the derivative of the function at a specific x value, c, we are instead going to use the first definition of the derivative, where it looks like this. The limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Now, how does this work? Well, f of x plus delta x just means I'm going to take x plus delta x and plug it in the function anywhere I see an x. So f of x plus delta x is going to look like this. Notice that I've just plugged in x plus delta x for x here, and that gives me f of x plus delta x. F of x is just x squared minus 3x. That's what we see up here. And then in our denominator, we keep that delta x. Now, how do we simplify this? Well, there's a bunch of things we have to do. First, we have x plus delta x, the quantity squared. So this we actually have to FOIL. You have to imagine it x plus delta x, the quantity, times x plus delta x. So you FOIL that, and you end up getting x squared plus 2x delta x plus delta x squared. Then over here, we distribute this negative 3 to the x and to the delta x. Over here, we can distribute the negative 1 to the x squared and to the negative 3x. So we get minus x squared plus 3x. Now let's start simplifying some stuff. So if we combine like terms, the negative 3x and the positive 3x cancel each other out. The x squared and the negative x squared cancel each other out. Now, notice that each of the three terms in the numerator, this is one term, this is one term, this is one term. Each of our three terms has a delta x. So I can actually factor that out from each of those terms. These delta x's in the numerator and denominator cancel each other out. And we're just left with the limit as delta x approaches 0 of 2x plus delta x minus 3. Now I can evaluate this limit by plugging in 0 for our delta x here. And I end up getting 2x minus 3. This is the derivative of this function right here. This is f prime of x.
My spidey sense is tingling. Must be time for a U-try.
Okay, doing the same thing. So we start with a. Again, it doesn't give you a point of tangency. It doesn't give you a specific x value that we want to find the derivative at. So we're not looking for a number. We're looking for a function. So we want the derivative of f of x, and we want it to be a function. So we're going to use the first definition of the derivative, which looks like this. This first part up here requires us to plug in x plus delta x anywhere we see an x up here. So it's going to be x plus delta x cubed plus 2 times x plus delta x. We then just plug in f of x, which is x cubed plus 2x, and that's all over delta x. X plus delta x cubed, we are going to have to FOIL twice. So you're going to have x plus delta x, the quantity, times x plus delta x, the quantity, times x plus delta x, the quantity. And that is going to look something like this. X cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. This right here, we distribute the 2 to the x and to delta x, so we get 2x plus 2 delta x. And then over here, we distribute the negative sign to the x cubed and to the 2x. Now, this looks crazy complicated, but we just have to combine like terms. So x cubed minus x cubed, those cancel each other out. 2x and negative 2x cancel each other out as well. So we're left with 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x. Now again, each term in the numerator has a delta x that I can factor out. This should happen every time. If you do this correctly, the delta x in the denominator should somehow cancel out. So here we can see that now the numerator and denominator have a delta x we can cancel out. And now we can evaluate this limit. We plug in 0 for delta x here, and we end up getting 3x squared plus 3x times 0, which just becomes 0, plus 0 squared, which is just 0, plus 2. So we get 3x squared plus 2. This is the derivative of this function. This is f prime of x. Down here, we just have g of x is equal to 8. This is our function. So we, again, use the limit process because we're not given a specific x value that we want to find the derivative of this at. So we use g prime of x is equal to the limit as delta x approaches 0 of g of x plus delta x minus g of x all over delta x. Again, this is just the same thing as the first definition of the derivative. So now we take x plus delta x and we plug it in the function anywhere we see an x. Oh, we don't see an x over here. It's just 8. So this is just going to be 8. And then g of x is just 8. So we end up getting 8 minus 8 over delta x, which is just 0 over delta x, which is just 0. So that means that the derivative of this function, g of x is equal to 8, is just 0. And that makes sense because if I were to find the derivative of this, or the slope of the tangent line of this, this is just a horizontal line, meaning that the slope of this line would be 0 because it's a horizontal line. So that makes sense why the derivative is equal to 0. Now, example 3 says find the derivative of the function by the limit process, so we're doing the same thing. The only difference is our variable is t instead of x, but it works the exact same way. So, to find the derivative, because we're not finding a derivative at a specific x value, or the slope of the tangent line at a specific x value, we're going to use the first definition of the derivative, which is just f of t plus delta t minus f of t all over delta t. Again, it's just t instead of x. It works the exact same way. So, f of t plus delta t means we're going to take this function and plug in t plus delta t anywhere we see a t. So it's going to be 2 over t plus delta t minus f of t, which we know is 2 over t, all over delta t. Now, how do I simplify a complex fraction? That just means there's fractions within a fraction. I need both fractions in the numerator to have a common denominator, so I'm going to multiply this fraction by t over t, and this fraction by t plus delta t over t plus delta t. I then multiply in the numerator over here. 2 times t, I get 2t. Over here, 2 times t gives you 2t. 2 times delta t gives you 2 delta t. Again, you have to distribute this 2 to the t and to the delta t. Now, both of these fractions have a common denominator, so I can subtract the numerators. It's going to be 2t minus 2t minus 2 delta t. Again, don't forget to distribute this negative to the 2t and to the 2 delta t. So 2t minus 2t, those are going to cancel each other out, and we're just left with negative 2 delta t up here. So now I'm going to rewrite this so it makes a little more sense. Instead of all over delta t, I'm going to rewrite it like this. Divided by delta t. It means the exact same thing as this up here. But you see that instead of dividing by delta t, I'm going to multiply by the reciprocal. It means the same thing. Why do I do that? Because these delta t's now cancel each other out. And I'm left with negative 2 over t times the quantity, t plus delta t. Now I can try to evaluate this expression. I'm going to take 0, plug it in for delta t, and simplify. What is t plus 0? That's t. What's t times t? That's t squared. So I get negative 2 over t squared. That is the derivative of this function. That is f prime of t. Part B, doing the same thing. Again, because we're not given an x value that we want to find the derivative at, or the slope of the tangent line at, or the slope of the function at, we are instead just going to use the first definition of the derivative, which is the limit as delta x approaches 0 of, in this case, g of x plus delta x minus g of x all over delta x. So now, we evaluate this by taking x plus delta x, plugging it in the function where we see an x. So g of x plus delta x is just the square root of x plus delta x plus 1. G of x, we know, is the square root of x plus 1, so that goes here, all over delta x. Now we simplify. How do I simplify this? Well, we're going to multiply the numerator and denominator by the conjugate of our numerator. So instead of having a minus in here, it's going to have a plus. Now, how does that help us? Well, if I were to FOIL this numerator, this times this, they're the same thing, so the radical disappears. This times this, and this times this, those are opposites, so those are going to cancel each other out. And then lastly, negative rad x plus 1 times rad x plus 1 just gives you negative x plus 1. So we get something that looks like this. Now we go ahead and distribute that negative to the x and to the 1. We combine like terms, so x minus x, those cancel each other out. 1 minus 1, those cancel each other out as well. And you see, we didn't distribute this delta x because what happens is this delta x cancels out with this delta x, and you're just left with 1 over rad x plus delta x plus 1 plus rad x plus 1. Now we can evaluate this limit by taking 0, plugging it in for delta x, and we can simplify. X plus 0 is just x, plus 1 is x plus 1. So we end up getting rad x plus 1 plus rad x plus 1, which is 2 rad x plus 1. And you're done.